Bismillahirrahmanirrahim. Assalamu alaikum dear students. Today is our 22nd lecture of Discrete Structures CSC 102. In the previous lecture we have studied functions. We have finished, you can say, functions. We have today we are going to start sequences and summation. In today's lecture we shall discuss some basic definitions of sequences, alternating sequence, and we shall also discuss some summations, summation notation, product notation and their properties, and at the end we shall discuss, if we have time, factorial notations. So what is basically a sequence? In daily life you encounter sequence of cars, sequence of anything, but in mathematics we shall study sequence of numbers, usually sequence of you can say integers. For example, the very simple sequence is 2, 4, 6, 8, 10, 12, 14 and so on. A sequence basically is a set of numbers in which there is a relation between every number. For example, here the next number in this sequence, this is basically a sequence of even numbers. The next number is obtained by adding 2 in the previous number. If we add 2 plus 2, we get the next term, and again the next term is obtained by adding 2 in the previous term. The next term is again obtained by adding 2 in the previous number. So there is a relation between these numbers. So such type of expression or set of numbers is called a sequence. There are many other sequences. For example, -1 1, -1 1, -1 1, and so on. So there is a relation between these numbers also. For example, this we can take 1 minus 1 1 minus 1 and so on. This is a sequence of number, and this number basically next number is obtained by, you can say, the powers, integral powers of the previous numbers. For example, here we can say that minus 1 power 0 is 1, minus 1 power 1 is minus 1, minus 1 power 2 is plus 1, and minus 1 power 3 is minus 1, and minus 1 power 4 is plus 1. This. So each next number of a sequence is obtained with the help of the previous number. Another example of a sequence is 1 over 1, 1 by 2, 1 by 4, 1 by 8, 1 by 16, 1 by 32, and so on. Here this term must be excluded from this sequence, or you can say this. Another example of the sequence is 1 by 2, 1 by 4, 1 by 8, 1 by 16, 1 by 32, and so on. Each next term or next term of a sequence is obtained by multiplying the previous term by 2. For example, this is 1 into 1 by 2, next is 1 by 2 into 1 by 2, next is 1 by 4 into 1 by 2, next is 1 by 8 into 1 by 2, and so on. So the next term is obtained by multiplying, adding, subtracting, taking power of the previous term. By adding, subtracting, multiplying, or taking power of the previous term by some number or something like that. In short, in sequences the next term is obtained with the help of previous term by multiplying by some number, by adding some number, by subtracting some number, or by taking power. So such type of expressions in mathematics is basically are called sequences. Each term of a sequence is basically, now we discuss some notations. Each term, for example, this is the first term, second, third, and so on. The first term of a sequence is basically usually denoted by A1, A0, or it starts with, it depends, it starts with 0 or 1. The first term of a sequence is denoted by A1, the second by A2, third by A3, A4. These 1, 2, 3, 4 are basically subscripts, and we read it as A sub 1 or subscript 1, A sub 2, A sub 3, A sub 4, and so on. So there is a general term of a sequence also. For example, here we can write the general term of a sequence by we will discuss it after defining the definition of a sequence. What is the general term, how we define it. So now we discuss what is basically the sequence and what is its definition. A sequence is a function. Basically, we have just finished the functions in the previous lectures, and you all know what is a function. A sequence is a function whose domain is either all the integers between two given integers, or all the integers greater than or equal to a given integer. This definition is taken from the book of Discrete Mathematics written by Susanna. There are some other definitions of sequences. Like a sequence is a function whose domain is the set of natural numbers. A sequence is a function whose domain is the set of you can say non-negative integers, and there are the different definitions in different books, but we can say that a sequence is a function whose domain is the set of non-negative integers. This is the most common definition of a sequence. Here, according to this definition, a sequence is a function whose domain is either all the integers. It could be negative numbers, it could be 0, it could be positive numbers, or all the integers greater than or equal to some given integer. Means here we can write this if we say that the integer, the terms of the sequence starts with 10, then this term will be A10, this term will be A11, this term will be A12, and so on, like this. So now the terms of the sequence basically are usually denoted by AM, where M is any integer, where M belongs to Z, and this is some particular integer, 2, 5, 10, 0, -3, -10, anything. All the next terms are denoted by M, M plus 1, M plus 2, M plus 3, and so on. If the sequence is finite, then the last term is AN. If sequence is infinite, then the sequence continues up to the infinity. Each individual term in the sequence, each individual you can say term is called the element of a sequence or term of a sequence, and is denoted usually by AK or AN or AI. There are different notations, and this is read as A sub K and is called a term. So this is a term, this is a term, this is a term. All the numbers in the sequence basically are called term. The K in AK is called a subscript or index of that sequence. So this is basically the definition of a sequence. So how a sequence is a function? For example, in the previous here we have defined a function, a sequence. Now how can we show that this sequence is a function? Now the sequence is basically 2, 4, 6, 8, 10, 12 and so on. Now if we define a set of natural numbers, for example this, if we take set of natural numbers as a domain, or you can say the set of positive integers z plus, then this set contains 1, 2, 3, 4, 5, 6 and so on up to infinity. And the second set is again the set z of integers, or you can say the set of positive integers, set of natural numbers. Then here we again have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 and so on. Now you can see here that if we take 1 here, 1 is related to 2, 2 is related to 4, 3 is related to 6, 4 is related to 8, 5 is related to 10 and so on. Now you can see that this arrow diagram basically satisfies all the properties of the function, because each element has some image and each element of x is connected to exactly one element of the second set. So this satisfies the definition of a function. So we can say that this is basically a function. How we can, this is basically a function which is defined on infinite sets, so there must be some formula which specify this function. So if we say that this an or ak, for example ak, as we have in the definition we have we said that the sequences are denoted by ak. So this is a function from z plus to z plus, and ak is defined by the formula. When we operate ak on any element k of z, it gives us, it is basically 2k. So you can see that here now we can obtain all the terms of the sequence. This sequence terms are basically ak of k, or you can say this 2k. If we put k is equal to 1 here, the domain, we obtain the first term. K is equal to 1, we get 2 into 1, 2. If we put 2 here, we get 2 into 2, 4, the second term of a sequence. If we put 3 here, we get 6, the third term of a sequence. If we put 4, we get 2 4s are 8, the fourth term of a sequence, and so on. So by inserting all the elements of this set here, we obtain all the terms of the sequence here. So this is how we can say that a sequence is a function. So therefore, as we have defined in the definition, basically a sequence is a function. Therefore all the sequences are basically the functions whose domain we have to decide what should be the domain of this sequence. As in this sequence I have guessed or judged, you can say that the domain of the sequence should be natural numbers, and we can define a formula this which could express this sequence, which could express the relation between the elements of domain and range. Now this formula, basically this is called the general term. Here we can write the general term of a sequence as 2k. So this is basically called the general term or kth term, or if it is defined as an zn z plus to z plus, an of n is equal to 2n, then it is here we must have 2n, and this is called nth term. Defining here the subscript is not important, it could be changed. So because if we define n here, if we define k here, it doesn't matter. We have to insert the elements of z here, then we obtain the elements of the terms of the sequence here. This will be the same. So we can say that all the sequences are basically are functions, and we can define a general term or a formula which represents the relationship between the elements of domain and range. Now, how to find terms of the sequence if we are given a general formula of the sequence? Usually the general formulas of the sequence here, as we have defined here, ak of k is equal to 2k, an of n is equal to 2n. These are usually denoted by ak is equal to 2k. There is no need to write it like this, ak of k is equal to 2k, because it is obvious that it is ak of k. It is obvious. We abbreviate it, or we write it in short as this. So now if we are given a general term of a sequence, how we recover the sequences from the general terms? If we are given two sequences here, ak is equal to k over k plus 1 for all integers k greater than or equal to 1. Now here they have defined the domain. For example, if we have a general term ak is equal to k over k plus 1, here they have given for all integers k greater than or equal to 1. So this is basically, they have defined the domain of the sequence, or they have given the domain of the sequence. For example, if we have here ak, this sequence, for example, this is basically a function ak from the z plus to it may be some rational number, so we define it now from z plus to you can say r, because this number could be non-integer, because if we put 1 here, we get here 1 plus 1 2, 1 by 2. 1 by 2 is not an integer, it is rational number, or you can say in general a real number. So now the domain is basically starting from 1 to all the integers which are greater than or equal to 1, means 1 2 3 4 and so on. And here we shall get if we put 1 here, we get 1 by 2. If we put 2 here, we get 2 by 3. If we put 3 here, we get 3 by 4 and so on. So we have a relationship between these numbers. The other real numbers are also present here. I have just written on the terms which comes by inserting k here, Now this is basically a function. In short, we write it like this. Here this is basically defined as the domain of this sequence. Now we are given the general term, and we have to recover all the terms of the sequence. So here the question is, compute the first 5 terms of both sequences. If we put k is equal to 1 here in this term, we get a1. Here k is equal to 1, here 1 plus 1, this is 1 by 2. If we put 2 here, we get 2 by 2 plus 1, which is 2 by 3, and 3 by 3 plus 1, 3 by 4 and so on. We can recover, we can obtain all the 5 terms of this sequence. Similarly, we have this sequence bi. Here I have told you that the variable is not important. We can define any variable to to write the general term of a sequence. Here we have written k, here we have written I, bi, I minus 1 over I for all integers I greater than or equal to 2. Now the domain is basically all integers greater than or equal to 2. Now the domain is of this sequence bi is 2, 3, 4, 5, 6 and so on. The range depends on this formula, whatever this is defined. This is basically I minus 1 by I. If we put 2 here in this I, we get the first term b2, which is the first term is basically now b2 here. If we put 2 here, we get 1 by 2, because 2 minus 1 is 1, 1 by 2 is, we get 3 is 3 by 2 by 3 and so on. We can find the next terms of the sequence. Here if we put 2 instead of in place of I, we get 1 by 2 by 3. If we put 3, we get 3 minus 1 by 3 and so on. We can recover the first 5 terms of the sequence. We can go further also. We can find all the terms, or because this is an infinite sequence, so we are unable to find all the terms of the sequence, because we continue inserting the integers 2, 3, 4, 5, 6, 7, 8, 9, 10 and so on. We get the successive terms of the sequence up to infinity. So this is how we can recover the terms of the sequence by using the general given formula. Another example is here, which is the alternating sequence. An alternating sequence is that sequence in which we get, for example, here compute the first 6 terms of the sequence C0, C0, C1, C2 and so on, defined as this here. Now the general term of a sequence is given, the domain is also given here. Now this sequence is a sequence in which we have defined Cj is equal to minus 1 power j. If we put j is equal to 0, we get minus 1 power 0, which is 1. If we put 1, we get minus 1 power 1, which is minus 1. If we put 2, we get minus 1 power 2 plus 1 and so on. We get the first 5 terms of the sequence. In this sequence you can see we get 1 minus 1, 1 minus 1, 1 minus 1. So the terms are repeated with the alternating sign. So such type of sequence is called basically alternating sequence, in which we have the same number but the signs are changing alternatively. So such type of sequence is called alternating sequence. So we can recover the terms of the sequence by using given general formula or general term or nth term. Here we have jth term. Next is how to find a general term of a sequence from given sequence. The general term is also called explicit formula. Here we can say it. Now we are given a sequence and we have to find the general term of this sequence, or kth term or nth term, or we have to find the explicit formula of this sequence. So here is the sequence which is given to us. First you investigate how the next terms of the sequence are obtained using previous terms. Now here we have 1, here we have minus 1 by 4, here we have 1 by 9, here we have minus 1 by 16. So how we can find the general term? We observe here what is happening in the next terms. Here we have 1 by 1, for example. Here we have minus 1 by 4, 1 by 9, 1 by 16, 1 by 25, 1 by 36. So first thing I have observed in this sequence that in the denominator we have squares of the integers. For example, this one can be written as 1 over 1 square. This is 1 over 2 square. 1 over 2 square is 4. 1 over 3 square. 3 square is 9. 1 over 4 square. 4 square is 16. 1 over 25. This is 5 square. This is 6 square. So this is the first thing I have observed in this sequence. Writing an explicit formula or general formula of the sequence is not an easy task. You have to observe what is happening in the sequence, how the next term can be obtained by using some rule, or some rule you can say. So in this sequence the next term is not very much related to the previous term. So there are sequences in which the next terms of the sequence cannot be obtained by using previous terms. So there must be some explicit formula, or there must be some relation between the domain and the range of the functions. So first we write it 1 over 1 square. Here we write it minus 1 over 2 square. This we write it 1 over 3 square. This we write it minus 1 by 4 square, plus 1 by 5 square, minus 1 by 6 square. So this is basically the first term, this is second term, this is third, fourth, fifth and sixth. We can write it as. Now we observe here that the sign is changing. We have plus, minus, plus, minus, plus, minus. So there must be plus minus in the numerator, and in the denominator we have k square, where k is basically starting from 1. Where k is starting from 1, we can say here k is greater than or equal to 1. Now the explicit formula or the general formula must be general, means if we put the values of the domain in this formula, we must obtain the successive terms of the sequence. Here if we put 1, we get plus or minus 1 divided by 1. Here, until here we haven't defined what type of term we write here in the numerator, so that we automatically get here plus 1 and here in the next term minus 1 or whatever comes in the numerator. In the denominator it's okay, if we put 1 we get 1, if we put 2 we get 2 square, which is 4, if we put 3 we get 3 square, which is 9. And in the denominator terms we have written k square, but in numerator what comes? So in numerator we can see that we have plus 1, minus 1, plus 1, minus 1 and so on, and and the sequence is starting from 1. So if we write in the numerator minus 1 power k, what happens? If we put 1 we get the first term as minus 1, which is plus 1. If we put 2 in the numerator we get plus 1, where we have minus 1. If we put 3 we get minus 1, here we have plus 1. So we have succeeded to, not really succeeded, but we have up to some extent define a numerator which gives us alternating sign, plus minus 1, plus 1, minus 1, plus 1. Now we have to improve it to get exactly plus 1 here, minus 1 here, plus 1 here, minus 1 here. If we write in the numerator as minus 1 power k minus 1 or plus 1, now we check it. If we put 1 here, we get minus 1 power 2, we get plus 1 here. If we put 2, we get minus 1 power 3, we get minus 1 here, because minus 1 power 3 is minus 1. If we put 3, we get 4 here, we get plus 1 here. So now we have succeeded completely in writing the numerator term. We have already written the denominator term. So now if we write this formula, this general term exactly expresses this sequence, and the domain must be greater than or equal to 1. So now we are succeeded in writing the general term, or the explicit formula which expresses the given sequence. So this is not necessary that there is only one explicit formula for a given sequence. There may be some other explicit formulas which can express this sequence. For example, if we write this formula and we start the sequence with k greater than or equal to 0, then we get the same sequence. If we put 0 here, we get minus 1 power 0 is 1, and we get here 1 square. If we put 1 here, we get minus 1 over 2 square. So for example, here we put 0, we get 1 over 1. We get, if we put 1 here, we get minus 1 over 2 square. Similarly, 1 over 3 square, minus 1 over 4 square, and so on. So we get the same terms. So these are two different explicit formulas which express the same sequence. But what is the difference between these two formulas? The difference is the domain. Here the domain is starting from 0, here the domain is starting from 1. So here, because the first, this is basically A0, this is A1, this is A2, this is A3. But here in this case, this sequence is starting from A1. So there is a difference between notations, but in general the sequence is, we obtain the same sequence. So we conclude here that for one sequence we can write more than one general terms or more than one explicit formula which expresses the same sequence. So this is how we can write a explicit formula or general term from a given sequence. So this is all your observation, how you write the explicit formula of a sequence. So next is a summation. Now what is summation? If we add up the terms of a sequence, we get the summation. For example, here in the sequence you have terms, there is a comma between the terms. In a sequence, the terms, the successive term is obtained by some rule, by applying some rule on the previous terms, but we do not add up the terms of the sequence. Now if we add up the terms of the sequence, we get a series, or for the time being we only say it a summation. Now if m, what is the definition of the summation or series? If m and n are integers and m is less than or equal to n, the symbol sum or summation, this symbol basically represents the sum. It is called sigma, and we write the variation of the index starting from below, k from m to n. It means that the terms of the sequence from m to n are adding up. So this is read as summation from k equals m to n, of a sub k is the sum of all terms basically from this k. Here we have ak, so the variation of k is basically starting from m to n. We can put here the values of k from m to n. For example, if we write here, this is an example, if we have a summation here, sum k from 1 to 5 of k square, it means we put k is equal to 1 here, plus k is equal to 2 here, plus k is equal to 3 here, plus k is equal to 4, plus k is equal to 5. Here we put just like this. What does it mean? This means this. It means summation k from 1 to 5 of k square. So this is how we can define the summation, where k is the index of summation, m is the lower limit of summation, n is the upper limit of summation. We write always the lower limit here and upper limit here. It means that k can vary from 1 to 5, and we insert k, all the values of k here in this, the general term of a sequence, you can say. So this can be expanded like this: 1 square plus 2 square plus 3 square plus 4 square plus 5 square, which is 55. This is basically called the expanded form of the summation, and this is contracted, or you can say the summation notation. Now, how to compute these summations? Let a1 is equal to -2, a2 is equal to -1, a3 is equal to 0, a4 is equal to this, a5 is equal to 2. Compute the following. Now, in this exercise, they do not give us the general formula of ak, but they have given the terms explicitly here: what is a1, what is a2, what is a3, and so on. Now, why we have to calculate this summation k from 1 to 5 ak? What is the value of this? First of all, we have to expand it. K can take the values from 1 to 5, so we put k is equal to 1 here, we get a1, plus then we put k is equal to 2, we get a2, a3, a4, and 5, a5. Now we use these values. a1 is what? -2, a2 is -1, a3 is 0, a4 is 1, a5 is 2. We put the values here and we sum up these values and we obtain the answer, which is 0. Now, what happens if we have k is equal to 2 to 2? What does it mean? It means k can vary from 2 to 2. It means that k can take values, k can take only the value which is 2. Summation k from 2 to 2 means ak, this is equal to only 2, because k can take value 2, so which is a2 is -1, so we obtain -1. So what does it mean now? Here we can define the summation like this also: summation k from 1 to 2. Here we have defined a to k. Here the subscript is basically scaled, you can say that a to k. Now if we put k is equal to 1 here, we get a2, 2 into 1. If we put k is equal to 2, we get a2 into 2, which is 4. So we take the sum of a2 and a4, so a2 is -1 and a4 is +1, so we get 0 here. So in summation we can scale the subscript also. So this is how we can expand a summation. This is how we can expand a summation in the expanded form. Now summation notation to expanded form. This is another example of the summation, which is here some, you can say, difficult summation notation. Summation from I from 0 to n and minus 1 power I over I plus 1. The index of a summation is not important, as the index of a sequence is also not important. Here we can define it as k from 0 to n. But here the index here is changed now. First we have here in I, here we have k. So now we have to write minus 1 power k divided by k plus 1. We have replaced I by k. We have replaced I by k, so we changed I by k everywhere. If we expand this or this, we get the same answer. Here I from 0 to n means I can take the values from 0 to n. N is any arbitrary integer, you can say. So first we put I is equal to 0 everywhere in this term, plus I is equal to 1 everywhere in this term, plus everywhere, plus I is equal to 2 everywhere in this term, plus so on. At the end, the upper limit, we replace I by n everywhere. So this is basically the expanded form of this expression of summation notation. So if we expand this one, we get the same answer, k from 0 to n. If we take k is equal to 0, we get minus 1 power 0 divided by 0 plus 1. Like this, we can obtain the same expression which we have obtained in this case. So we have concluded here that in the summation notation, the index of the summation is not important. We can change the index. Now expanded form to summation notation. How we can write a given expanded form into a summation notation. This is again involve the observation, the personal observation, how you write the summation and how you take the index and how you take the variation of index. The general term of this summation, basically how we can write the general term of this summation. Here you can see that we have 1 over n plus 2 over n plus 1, 3 over n plus 2, n plus 1 over 2n. So how the next term is obtained by the previous term, or what rule can be applied here to obtain a general term? Here in the numerator you can see that we add 1 always. We add 1 always. 1 plus 1 2, 2 plus 1 3, 3 plus 1 4, and so on. General n plus 1. In the denominator we again add 1 always. N plus 0, n plus 1, n plus 2 means n plus 1 is obtained by adding 1 in the previous term. Next term here n plus 2 is obtained by adding 1 to the previous term, and so on. So the rule we have understand. Now we have to write the general term of the summation. If we write here in the numerator k plus 1 and in the denominator k n plus k, because we add 1 to obtain each successive term. And now we have to decide what should be the variation of this index which we have added here in the general term k. If we put k is equal to 0, for example, here we can obtain the first term. If we put k2, we can obtain second term. If we put k is equal to 3, we can obtain third term, and so on. At the end we should put k is equal to n, so that we shall obtain this term. If we put k is equal to n, then we obtain n plus 1 over n plus n 2n. So now we can write the summation notation, this expanded form into summation notation. So this is equal to summation k from 0 to n, k plus 1 divided by n plus k. So this is basically the summation notation which expresses the given summation, this given expanded form of the summation. So this is how we can write an expanded form into a summation notation. This all again involves your personal observation, how you write the general term, how you decide the variation of k. It can vary also. Now we have to write this expression into the summation notation. Now this is basically what is the value of this expression when n is equal to 1, n is equal to 2, when n is equal to 3. This is again an important point here about this summation notation and sequences. Either it is a sequence or it is a summation, we do the same process. When n is equal to 1, we can obtain, this is basically the general term, or you can say the nth term of this summation. How, when n is 1, we must obtain only the first term. When n is 1, we put 1 here, here we put 1, we get 1 over 1 into 2. So the summation must be stopped here. These terms, the other terms, this will not come in when n is 1. When n is 1, the expression equals 1 into 1 by 2, 1 into 1 into 2, which is 1 by 2. When n is 2, we must get until 1 over 2 into 2 plus 1, this is 1 by, we get the first two terms. We must have first two terms, because if we put 2 here, we get 2 into 2 plus 1, 3, 1 by 2 into 3. So the summation must be stopped until here. When n is 3, we must get first 3 terms of this summation, because if we put 3 here, we get 3 into 4. So we must get the first 3 terms of this summation. So here it is given. Next is a telescoping sum. Some sums can be transferred into telescoping sums, which then can be rewritten as a simple expression. For instance, we observe that if we write 1 over k minus 1 over k plus 1, if this is a sequence given to us, a, k, or the nth term of a sequence, which is 1 over k minus 1 over k plus 1. Such type of general term of sequences basically can be simplified by taking here by doing some simple algebra. So if we take the LCM here, k into k plus 1, then we get k plus 1 minus k, and we obtain this 1 over k into k plus 1. So if we are given such type of nth terms of a sequence or a summation notation, we can simplify them to such type of expression. And if we are given such type of expressions, then we can transform them into this form to simplify the summation which is given to us. Now, expanding this form of the summation is a bit difficult or a bit tedious. If we expand this form, we shall expand all the terms and then take the LCMs, and it involves a lot of calculations. So if we are given such type of summations, we can transform them into this form by using some simple algebra. And then if we expand this form, we can easily obtain this, because k is varying from 1 to k is from 1 to n, and we have 1 over k minus 1 over k plus 1. If we put k is equal to 1, we get 1 over 1 minus 1 over 2 plus 1 over 2 minus 1 over 3 plus 1 over 3 minus 1 over 4, and so on until this. Minus 1 over 2 can be cancelled out with plus 1 over 2, minus 1 by 3, plus 1 by 3, minus 1 by 4, there must be some here, plus 1 by 4, and similarly minus 1 by n with plus minus 1 by n with plus 1 by n. This can be cancelled out, and we obtained this 1 minus 1 over n plus 1. So this is basically simplified. Wherever if we try to solve this summation, it involves a lot of calculation. So such type of summations are called a telescoping sum, in which we can cancel out all the terms between first and final. So such type of sums are called telescoping sums. The next is the product notations. As we have defined the sums of the terms of the sequences, we can define also the product of the terms of the sequences. If m and n are integers and m is less than or equal to n, the symbol this symbol read as the product from k equals m to n of a sub k is the product of all terms of the sequence from m to n, and we write it as this. Just like the summation, here we write dot, which represents the multiplication, instead of sum, which is plus. So a recursive definition of the product notation is also can be defined as this. If we have k is equal to m to m, ak is only the first term, and this basically can be defined as k is equal to m to n, ak is equal to k from m to n minus 1, and we write the last term separately. So this is basically the recursive notation of the product of the terms of the sequence. For example, compute the following products. Here we have product k from 1 to n of k. Now what it means, k varies from 1 to 5, and we put k is equal to 1 first, then k is equal to 2, k is equal to 3, k is equal to 4, k is equal to 5, and we multiply all these terms, which is 120. Similarly, we can get this product k is equal to 1 to 1, which is only k can take only one value, which is 1. So this is 1 over 1 plus 1. So this is how we can define the product notations. Now, properties of summation notations, you can say, if we have two sequences am plus 1, am plus 2, and so on, bm plus 1, bm plus 2, and so on, then we can define sum k is equal to m to n ak plus sum k is equal to m to n bk. This can be defined as this. One thing that is notable here, that the summation here and summation here, they have same variations, they have same index. The index could be different, but the variation must be same. Then we can take out the summation here. So we can define the summation like this. This is the first property. The second property tells us that if we multiply some constant by the summation, then we can multiply this constant with each term of this summation. The product notation, the property of product notation is that product k is equal to m to n ak and product k is equal to m to n bk, where ak and bk are two different sequences, we can write them as this, as a product of whole ak into bk. But the same thing here is that the variation of the index must be same in both product notations. For example, here we have summation k is equal to m to n ak plus 2 summation k is equal to m to n bk. AK is given k plus 1 and bk is given k minus 1. Then how can we define the sum of these two summation? So AK is k plus 1, 2 comes as it. This terms, here we write k plus 1, here we write k minus 1. 2 comes as it. And now, as you can say that the indexes and the variation of the summation are same in both terms, we can take the summation out here as a single summation, and we can add up the internal terms and we can simplify them like this, and we obtain the summation of summation of two different sequences. Similarly, the product notations, AK is k plus 1, BK is k minus 1. We can take the product outside here and we multiply both these, k plus 1 into k minus 1, and we obtain this k square minus 1. So for today it is I think enough. Today we have discussed sequences, some basic definition of sequences, alternating sequence, summation notation, product notation, and their properties. In the next lecture we shall continue discussing the change of variable, how can we change the variable in the summation and product notations, and also we shall discuss the factorial notations. Until the next lecture, Allah Hafiz.